Hi, welcome. Why does something exist instead of nothing? What are dark matter and dark energy? Is the universe infinite? These are among the most profound questions in modern cosmology, and scientists are striving to uncover answers. Over the past decade, an extraordinary idea has gained traction among astrophysicists, the notion that our expanding universe is not unique. Instead, it may be one of countless others, a vast multiverse, rather than a singular universe. The multiverse. We have some fascinating ideas, many rooted in the concept of the multiverse. According to this theory, our universe, governed by familiar physical laws, is just one bubble among countless others that emerge and vanish within a larger metasystem of multiverses. If true, this framework allows us to identify a beginning for our universe, as it would have arisen from a larger structure generating and recycling universes. However, this simply shifts the question, how did the multiverse itself come into being? Alternatively, could the multiverse have always existed? While this idea may be philosophically unsettling, it challenges us to remain open-minded. After all, quantum mechanics once seemed bizarre when first introduced in the 1900s, yet it turned out to be true. Similarly, just because something seems strange doesn't mean it isn't possible. Dark energy. The fate of the universe hinges on its energy density. It might contain enough energy to halt its expansion and eventually collapse back on itself, or it might have so little that it will continue expanding forever. One thing seemed certain, gravity would slow the expansion over time. Although this slowing hasn't been observed, theoretical models suggested it was inevitable, as the gravitational pull of matter should draw everything together. Then came 1998. Observations from the Hubble Space Telescope revealed something astonishing. Distant supernovae showed that the universe expanded more slowly in the past than it does today. Instead of slowing down due to gravity, the universe's expansion is accelerating. This unexpected discovery left scientists searching for answers. While theorists proposed various explanations, the true cause remains unknown. They have named this mysterious force driving the acceleration dark energy. Another major puzzle is dark matter, a hypothetical substance that makes up about 85% of the universe's matter. Its existence is inferred from calculations indicating that galaxies would not hold together, form, or move as they do without the presence of large amounts of unseen matter. Additional evidence comes from gravitational lensing, the cosmic microwave background, and observations of the universe's structure and galaxy evolution. Yet another unsolved cosmological mystery is the matter-antimatter asymmetry problem. This conundrum lies at the heart of our very existence, tracing back to the universe's earliest moments 14 billion years ago. Asymmetry. Approximately 13.7 billion years ago, the universe was far smaller, denser, and hotter, a seething soup where matter and energy were in constant interplay. Today, we take for granted that matter remains stable. You don't expect to suddenly transform into energy and dissipate into space. This stability arises because our environment isn't conducive to such events. However, in certain parts of the universe, like the core of a star or during the universe's earliest moments, such transformations occur routinely. At the origins of the universe, particles would spontaneously pop into existence from energy, only to recombine into energy again, a process that, while exotic to us, is natural under extreme conditions. As the universe expanded and cooled, energy began converting into matter. When temperatures were high enough, this exchange between matter and energy was a two-way street. However, as the universe continued to cool, the energy level dropped below the threshold needed to create new particles. If the process were perfectly balanced, all matter and antimatter would have annihilated, leaving behind only beams of light. But that's not the universe we see. Instead, there's a mysterious imbalance. For every 100 million matter-antimatter pairs, one extra matter particle survived. This asymmetry is the reason everything, stars, galaxies, planets, and all forms of matter, exists. The origins of this imbalance remain unknown, though scientists have some hypotheses. The annihilated particles left behind beams of light, some of which we detect today as the cosmic microwave background, a remnant of the universe's fiery beginnings. Why is there something? Why is there something rather than nothing? Is a timeless question about the fundamental nature of existence, pondered for millennia by philosophers. The Greek philosopher Aristotle posited that everything in the universe must have a cause, leading to the concept of an ultimate, uncaused cause. In modern times, physicists like Stephen Hawking and Lawrence Krauss have approached this question through the lens of quantum mechanics. They suggest that in a quantum vacuum state, virtual particles and spacetime bubbles can spontaneously emerge. This phenomenon, supported by mathematical models, implies that in an inflationary vacuum with a mass equivalent to a bag of sugar, the laws of physics allow matter to arise from nothing. However, this explanation raises another profound question: where do the laws of physics themselves come from? Even the answers we do have often seem mysterious when viewed from a cosmic perspective, such as the immense scale of the universe, where vast stretches of space exist simply because light travels at a finite speed. Cosmic perspective. The speed of light, traveling at 186,000 miles per second, is incredibly fast, but far from infinite. Its finiteness has tangible effects. For instance, during a phone conversation with someone on the moon, there would be a 3-second delay between speaking and hearing a reply. That's the time it takes for light to travel between Earth and the moon. It takes light 8 minutes and 20 seconds to reach us from the sun, 100,000 years to cross the Milky Way, 1 billion years to reach distant galaxies, and 13.7 billion years to traverse the observable universe. Light speed sets a measurable limit on how we perceive the cosmos. Now, consider this: the universe is 13.7 billion years old. Imagine an infinitely large universe, and place yourself at its center. Objects at the edge of the observable universe, 13.7 billion light-years away, are seen as they were at the moment of their formation because their light has only just reached us. Move closer, and you'll see objects in their younger stages, toddler years, adolescence, and so on, until you observe celestial bodies as they appear today. This limit to our view exists because the universe has a finite age and the speed of light is finite. As time passes, the horizon of the observable universe expands, allowing us to witness galaxies being born, even as others fade beyond our reach. What if, one day, the signature of the Big Bang, the cosmic microwave background, disappears? That would suggest our horizon has reached a region of the universe where no more galaxies exist, potentially revealing the true edge of the universe. Such mysteries compel us to explore, even if answers remain elusive. One of the most profound questions in cosmology is, what existed before the Big Bang? While we currently lack the means to probe this era, it's unwise to assume it will forever be unknowable. History shows that science has repeatedly broken through supposed boundaries of understanding. Each generation builds on the knowledge of its predecessors, often overturning what was once considered the limit of discovery. It's a humbling reminder that the pursuit of knowledge is an ever-evolving journey, and future thinkers may uncover answers to questions we cannot yet fathom. Thank you for watching. If you enjoyed the video, please press the like button, and if you're new, please subscribe and turn the notification button on so you don't miss our future videos.